solutions?
Yeah.
Okay.
So, let's see.
As I remember these from last year, for some of them, well, okay, I'm trying to remember issues that have come up on review sessions, but I don't know if we're, okay.
Well,
We'll just jump right in. Okay.
for example, this section where it says complete the square and give a substitution.
Oh, so,
I know it's not.
okay, so you're not in 7.5. Because 7.5 is numerical integration.
I'm sorry. Yeah, 7.4.
Say, boy, as hard as 7.1 through 7.4, I'm surprised that you're issued with 7.5.
Yeah.
Okay.
I saw the 7.5 at the top page. Sorry, yeah, 7.4.
Okay.
So this section, 27 through 33, where it's complete the square and give a substitution.
Okay.
I know it doesn't ask you to actually the integral.
Mm-hmm.
But I don't, for example, number 29. In the back of the book, they said you should substitute tan theta minus 3/2. And I got something close, but not exactly. And I can't tell if I'm doing it right because the answer's in the back.
Okay, so the idea is, if after doing algebra, we can turn it into something like this. So suppose after doing some algebra, it turns into something like that. Ignoring the fact that if it's like that, you could actually read it off the table. But the point is, where did the form go on the came from? So if you had turned it into something like this, then the substitution you want to make is t equals a times the tan. Because if you think of this as, if this was t squared plus 1, you'd want to turn it into t squared plus 1, because that would be secant squared. But since there's an a squared here, the way that we deal with this is make it a times the tan, because then this would be a squared squared. So this would be a squared tan squared plus a squared. When you factor out the a squared, it's a squared times tan squared plus 1. And that's the kind of thing you want, because that's a secant squared. And then t would be a secant squared theta. Well, that's a secant squared, and that's also a secant squared. So all you're really left with is 1 over a. So that's 1 over, well, but okay, we have to, the 1 over a is a constant, so like the log of a. So this would be 1 over a times theta. But what is theta? Well, in order to know what theta is, you need to know what tan of theta is. Theta is t over a. So theta is the arctan of t over a. So this would be 1 over a, the arctan t over a, which I think means we actually just showed the derivation of formula number, we just derived formula number 24, by the way. Okay, so if it's something like this, what we want to do is we want to replace t by a tan of theta. Now, if you were looking at a solutions manual, there's things that they could say that you're doing. They could say that you're replacing t by a tan of theta, or equivalently, they could say you're replacing t of a by tan of theta, or equivalently, they could say you're letting theta equal the arctan of t over a. I'm going to guess that the issue that you're having is you're looking at things in one form and the solution, it's more serious than that.
Yeah, I think.
Okay. Or another issue is that they might have made.
Yeah, well, it's more likely I made a mistake.
Well, I mean, at the risk of putting too much confidence in you, since you this over, I actually think there's a pretty good chance that you didn't make the mistake.
Well, let's see. So 29, they said the answer is y equals tan theta minus 3. And I got that y equals root 3 over 4 tan theta minus 3 half.
Well, let's play along and see where it takes us. So we complete the square, and at any point that I do a step, which isn't what you did, so it's y squared, so it's y plus 3 halves squared plus 3y plus 9/4 is left over. Well, 9 is left over, but we're supposed to go all the way up to 3, which is 12/4. So we have another 3/4. So I can do this in one step, or I can do it in 2 steps. In other words, I can put the tan into the y plus 3 halves, or I could first replace the y plus 3 halves by just substituting t. Do you want me to go straight to the trig substitution or not? Okay, I'll do it in 2 steps. Okay, so what I'll do is I'll simplify this and write that as a square. So let, say, x equal y plus 3 halves, in which case dx and dy are the same. So this is x squared, and since this is a positive number, it's a perfect square, not in the way that you think of it as 149. So the thing that's being squared is root 3 over 2. So if you complete the square and let x equal that linear term, we get x squared plus a squared, where a is root over 2. Does that look great? Does that look like we came up with? So the next thing is, we want this thing to be 3/4 tan squared. Because back to the 3/4 out of both. So we can write the substitution out in 2 ways. We could say the end result that we want is that x squared is going to be replaced by 3/4 tan squared. Or you could just immediately jump to the chase and say x is root 3 over 2 tan of theta. Because again, if you have x squared plus a squared, what we do is let x equal a tan of theta. When we do that, the bottom becomes 3/4 tan squared plus 3/4. So 3/4 tan squared plus 1. And that was the whole reason for making this substitution, because we wanted to get that tan squared plus 1. dx is root 3 over 2 secant squared theta d theta. So this is root 3 over 2 secant squared theta d theta. Now the reason we did all this is because we're going to get these secant squareds all over the place. So this secant squared cancels with that, because that's secant squared. And what we're left with is, let's just play around with the algebra a bit. We're left with root 3 over 2 divided by 3/4, which is root 3 over 2 times 4/3, which, depending upon how you want to write it, you can write this as 2 root 3 over 4, or 2 over root 3. So you can write it like this, or like that. Again, I don't know if this is the issue that you had, but I'm somehow suspecting that your issue isn't as serious as you think. We'll find out. So this over this, which form do you prefer, the top or the bottom? The top. The top. Okay, so this is just 2 root 3 over 3 theta. Well, this is a constant. Integral d theta is just theta. You just have to go back and figure out what theta is. Well, to figure out what it is, we need tan of theta. So according to this, tan of theta as you might have preferred it, 2 root 3 over 3. But x is holding the place of y plus halves. So that's 2 over root 3 x, which is y plus 3 halves. So the tan of theta is 2 over root 3 y plus 3. But again, I think you prefer this as 2 root 3 over 3. So I'll turn this into 2 root 3 over 3. Now I'll take our tan of both sides, meaning that theta is 2 root 3 over 3 plus 3 halves this expression, but I have to take the arctan of all this. So when all the algebra is done, theta becomes the arctan of 2 root 3 over 3 So now we have 3 answers that we can think about. Answer, your answer, and the book's answer. So how does this compare to yours and how does it compare to the book's?
That's the answer I got for when you actually solve the problem. Mm-hmm. But that's not what the book is asking. They just ask, and so they don't actually have an answer in the back for solving the actual problem. In the back is what the substitution would to compute the integral. Okay. And so they say that the substitution y equals tan theta minus 3 halves. But isn't it root 3 over 2 tan theta minus 3 halves?
Okay. So they're saying y equals, right, so it really should be, again, viewing this as 2 over root 3, it's y plus 3 halves is 3 over 2 theta, or y equals root 3 over 2 tan of theta. So they had this answer without the root 3 over 2?
Right.
They were wrong. Now you have to keep in mind that these huge, like 1,000-page manuals are not written by the authors. You're an idiot like me who writes some solution now. For the most part, they're written by the TAs or the graduate students, and I don't know how well read these things are better typeset, so mistakes like that. But you were right. They were wrong. I told you would probably. I mean, given the, I suspect that you probably tried this problem at least 3 times and came up with actually a final answer. And if your final answer works, it's kind of funny that how could my substitution be wrong? So I kind of figured.
But I didn't know that my final answer was right because they don't. So there's no way that you can check that you did it.
All right. Oh, that's why you're here. Okay. So you're feeling better about your answer now. Now, was there another one where they may potentially have messed up, or? Okay, what do you think? Should we give Barbara another question, or should we
give her another question? Okay.
Well, for 31, I don't think there's a mistake in the back of the book. This one I find really confusing, I think because of the negatives.
Okay. At the risk of sounding like double talk, you know why this problem is confusing? Because of the negatives. So, the reason that you found it confusing is exactly the thing that makes it kind of confusing. Okay, so that was enough double talk. So let's actually look at the problem. So that was the one with the DZ over 30? Was that 31?
31 is 4 over the square root of 30 minus z squared.
So the 4 is not too important, but it's there. Okay. So what we need to do is we need to play around with this 2z minus z squared. And we'll give it the treatment. the leading coefficient, complete the square, and see what we come up with. So this is negative, as you said, that negative sign is the problem, so let's pull it back. Z squared minus 2z. On the inside, I can play my complete the square game. So it would be z minus 1 squared. It's going to give me z squared minus 2z plus 1. To keep this what it's supposed to be on the inside, since this is now z squared minus 2 plus 1, I need to subtract the 1 away. And now, when I distribute the negative sign, it's 1 minus z minus 1 squared. At which point, I have two ways that I could solve the problem. So, are you okay up to that point? So the way that we handle the negative, because the problem is you don't like that negative greater than the first thing, the 2. So I pull the negative out, and then I have a quadratic z squared minus 2z. Then inside that I can complete the square. Then I can redistribute the negative at the end. So negative is a problem. I pull it out, do all the dirty work, then put the negative back in at the end. So I can sort of go two routes. To do it all in one step, I can replace that by squared. So I can replace z minus 1 squared. So I can replace z minus 1 squared by sine squared. Well, how do you replace z minus 1 by sine squared? By letting z minus 1 equal sine of theta. So this would be, and then dz is cosine of theta d theta. So this would be 4 cosine of theta d theta. This would be the square of 1 minus sine squared. Well, the whole reason we made the substitution is because 1 minus sine squared is equal to cosine squared. And then the square root of cosine squared is just cosine. So the denominator is just cosine, which cancels with that. And this just becomes the integral of 4 d theta, which is 4 theta. And if we go from here, theta, to get theta, we take the arc sine. So theta is sine of z minus 1. Or, if you wanted to do this in more steps, like once you were over here, so once you've got something like this, you don't feel comfortable making the trig substitution at this particular point, you could just let equal z minus 1, then dx is dz, and this becomes 4dx 1 minus x squared. Then you could go ahead and let x equal the sine of theta. And notice, essentially, this substitution is what happens if you combine those two substitutions. So the way that they phrased the answer was that they wanted z minus 1 is the sine of theta, or they wanted sine of theta. They wanted theta was the arc sine of z minus 1.
They don't actually solve the problem. The answer is just z equals sine of theta plus 1.
Oh, okay.
Give the substitution.
Oh, okay. So I said that z minus 1 was sine of theta. That's same as, okay. But if you say z is sine of theta plus 1, then you kind of wonder where it comes from. If you say this, then you can see where it comes from. But I mean, you were right. The troublesome thing with that one was the negative sign there. So the very first thing I did was factor it out and say, okay. And it's not just that I'm factoring out the negative sign. It's whatever number happened to be in front of z squared. In this case, it was -1. I factored that out because then I get a square term, and then I know how to complete the square. Because I'm going to complete the square, I want a 1 out of my square term. Other questions on this? Next question, then. Well, you'll figure something out while I raise the board.
Well, I'm sorry.
Oh, okay.
I don't mean to make this my personal beef.
Since no one else is asking a question, I mean, we certainly can't say that you're hogging. Otherwise, we'd just be sitting here with an awkward silence.
I can't have that.
No, we don't want that.
Okay. Well, for number 33, you don't actually have to do it, but my question is just more, so, like the rest of the problems in this section, they're asking you to complete the square and get the substitution so you can solve the integral. And so it's easy to complete, I mean, you can tell which square they want you to complete, but then I don't understand what the point of completing squares there, and I wouldn't know how to solve that integral, even though it's not what they're asking. If we don't need to know how to solve that integral, then I don't care.
Okay, so
okay. But like, but if we do, then
so here's the question. Because I think if they're asking you to complete the square, that's a misleading way to solve this problem.
Okay, then let's do it.
But it's a problem. But it's a problem you should be able to solve. Was it +7? Doesn't matter. But okay. When you're doing a problem, and I mean these problems are sort of telling you what to do. You're going to complete the square. You're going to make a trig substitution. But most integration problems, the real trick is to figure out what technique you're supposed to use. The first thing you tend to look for is it an obvious thing where I know the answer? That's not an obvious thing where I know the answer. So the next thing you tend to look for is there a substitution that simplifies things? Well, when you've got sines and cosines and exponentials floating around, a logical place to look for substitution is the thing that's plugged into the sine or plugged into the cosine or plugged into the exponential function. So, you've got something that's plugged into the sine. So there's something plugged into the sine. So what we'd really like is for the derivative of this thing to be what's left over. Well, what's the derivative of this thing?
2t + 1.
Well, that's precisely 2 copies of that. So in other words, this is a sine of something times its derivative. So if we replace, and so that's sort of the logical place to look for a substitution. If you don't know what to do when there's something plugged into a sine or a cosine or an exponential, that's a logical place to look for a substitution. So if we let u equal t squared plus 4t plus 7, then du is 2t plus 4 dt. Well, this becomes the sine of u. T plus 2 dt is what was left to replace. But notice we can turn this into t plus 2 dt by multiplying by 1. So 1/2 du is t plus 2 dt. So times 1/2 du and 1/2. All that's left to do is integrate sine. Well, we know the integral of sine is negative the cosine. So that's minus 1/2 the cosine of u. And u was simply a placeholder for t squared plus 4t plus 7. So I don't see why one would be tempted to complete the square problem?
I was not tempted to.
Okay.
But the book wanted me to.
I was just playing silly.
So generally when you complete the square is the purpose so that you can get it in a form to do a trig substitution?
Mm-hmm. And the trig substitution is sort of a resort. Because if you think about it, we were 7, 1, 7, 2, 7, 3, 7, 4. The trig substitutions are the last thing. So you try a trig substitution if you've got a quadratic and the more logical things haven't worked. I mean, the more logical are look for a straight substitution, see if perhaps integration by parts applies. Completing this square using trig substitution sort of if you're stuck. It's kind of and it's not quite a Hail Mary, but it's certainly far from the first thing that you do. And this is just a weird problem.
How many substitution questions are you going to answer?
I don't remember. Well, I think it's probably fair to say that probably 3, because there's the sine one and the secant one. But, then it becomes a matter of interpretation. For example, suppose I gave you a partial fraction problem. And in the partial fraction problem, you had to do something like that. Well, you could do that by trig substitution, replacing t squared by 4 tan squared. Or you could just say, yeah, I can do this by hand if I wanted, but the denominator is a t squared plus a squared, where a is equal to 2, and that's things on the table. So, yeah, you could do that by trig substitution if you wanted to.
So there are multiple ways for us to solve these problems.
There is always at least one, or oftentimes many.
Okay. So if we do something even more difficult, like we had completed the square for that one, which would have been ridiculous, but still come up with the same answer.
Okay, I'll give you an example, and this might be where Ashley was headed, that you might be expecting more trig substitution problems than there really are. And this again also relates to Barbara's question, in that since trig substitution is the last thing that you see, sometimes what people become tempted to do is anytime they see a quadratic, they're going to do a trig substitution. So, for example, you might have something like I'd say, oh, x squared minus 1. I can do a trig substitution because I can turn that to secant squared minus 1. But you have to say, no. We're dealing with rational functions here. If I'm dealing with rational functions, before I start dealing with trig substitutions, I'm going to say, this is a rational function. I have a fairly easy algorithm for integrating rational functions. Let's look at this one. First, I want the top to have smallest degree. Yep. Then I want the bottom to be completely factored. And, but if x plus 1 and x minus 1 is the factor in the bottom, I've got 2 choices in how to do this without using One is, you have a formula that comes from partial fraction decomposition that tells you how to integrate 1 over x minus a times x b. So you could use the formula for integrating 1 over x minus a times x minus b. A is 1 and b is negative 1. Or, it's not a hard one to do, you could actually just do the partial fraction decomposition and find a and b. So for something like this, these are all far more logical approaches than doing a partial fraction decomposition. The partial fraction decomposition, last resort, if you're stuck. And you certainly would not want to use trig substitution for something like that, even though there's an x squared minus 1 on the bottom, because unless it's something that's obvious, that's not necessarily obvious. So if something isn't obvious, then the first thing you try to do is there some substitution that will greatly simplify it? Well, is there a substitution that will greatly simplify this?
X squared minus 1.
Right, because the top is the derivative, not only almost the derivative, the top is exactly the derivative of x squared minus 1. So if you let u equal x squared minus 1, you try to do this by a trig substitution. Just let me see if it turns out to be particularly complicated. The bottom would become squared. The top would become secant times secant tan, which would be secant squared over tan, which would be 1 over cosine times sine over cosine, which would be cosine over sine. It's not too bad. But the point is, the integral of 2x over x squared minus 1, very first integrals you could do the moment you learn the substitution rule. It's far more complicated to do it by integration by parts. You could also do substitution. 2x over x squared minus 1 is also something that you could do by part decomposition, but you don't need to because it's so simple the way it is. So look for the simplest thing. I mean, go through your mind. Is it something which is obvious, like I know the answer in my head, or it's clearly on the table, or is there a simple substitution? And for 2x over x squared minus 1, there's a simple substitution. So look for the simple substitution before you look at complicated things. Because not surprisingly, again, since with the techniques of finding antiderivative, since trig substitutions are the last one that you do, and in some sense the hardest, I focus a lot of energy on it, and they're, they'll align to a hammer every problem nail. So if you finish studying the section on trig substitution, to every quadratic looks to you like a trig substitution problem. No, most quadratics will not require trig substitution.